welcome to the NPTEL course on power system protection. We are in the relay lab, fourth experiment. This is on distance relay performance evaluation. We have studied distance relay for line protection. Distance relay generally is being set for different zones, typically zone 1, zone 2 and zone 3. Zone 1 and zone 2 are for the primary protection of the line and zone 3 is for the backup protection of the adjacent line. In this demonstration, we will have the how the corresponding zone 1 performance is being achieved for a line protection. We have a physical line in the laboratory setup, 3-phase line, and we have 3-phase arrangements for the supply 400 volt, and then we have PTs and CTs connection, and those are connected to the distance relay. We make REL 511 and then we will go for the demonstration. For this we will first see the circuit connection and then we will create fault at the different positions of the line and see how does the corresponding relay perform. For that we have different settings in the relay also, and whether the corresponding relay performance is satisfactory or not, we can verify. So, in overall our coverage will be the background will be on the theory perspective, little bit on that, the corresponding circuit diagram and the different settings including the line parameters in the setup, and then we will go for the results and verification. So, the overall objective of this lab experiment on the distance relay is to verify zone 1 operation of the distance relay REL 511 ABB make. So, as already mentioned, we will have the corresponding voltages and currents input to the relay through the PTs and CTs, and we will create faults, and then we will see that how good is the relay in performing the decision for the zone 1 fault. We know for phase to ground fault or any phase to ground fault, the corresponding relation for Z apparent for this is becomes V m upon I m plus k naught I naught, where the 2 bus systems if we have considered, then the relay at R m, distance relay at R m takes care of this line. So, for zone 1 we consider typically 80% and the rest portion is taken care by the zone 2, and then subsequent portion in the system adjacent lines are being taken care by zone 3. So, we know that the corresponding Z apparent computed by the relay at this point is the V phasor of that corresponding faulted phase upon the corresponding faulted line current plus this K naught, the I naught, the 0 sequence current, where the K naught equals to the 0 sequence compensation factor, and that becomes equals to Z 0 minus Z 1 upon Z 1, where 0 stands for the 0 sequence component and 1 stands for the OD sequence component. This can be in terms of the whole complete line impedance or per kilometer line impedance also. So, that we have already discussed in details in the theory. So, for this case our verification will address only phase A to ground fault or phase B to ground fault or phase. So, only phase to ground fault we will analyze. One can go for the different types of fault and different positions of the fault similarly. So, we have a circuit connection for this. So, what we see here, this represents our transmission line model. So, we have in this setup 3 coils inductance. So, these inductance they have their own inductance and resistance associated. So, that is our transmission line model, and they are not mutually coupled, we will show in the system also. So, therefore, the corresponding Zm value between phases here happens to be 0, and that is the reason the corresponding 0 sequence impedance of the line becomes equals to the positive sequence impedance of the line, that becomes equals to the negative sequence impedance of the line. These three phases are connected to the loads. In the load we have resistive load, ball loads we have connected for that perspective. The lines has different sections. So, we can have the tappings and create faults, or you can load in the intermediate points also. These lines are fed from 3 phase supply here, 400 volt supply, and this 50 hertz system through a conductor circuit breaker arrangement, and the corresponding currents and the voltages are fed to the relay. So, this is our relay, distance relay REL 511 box. So, this relay is being fed to this corresponding currents are being fed through the CTs, a set of 3 CTs are there, 25:5 ampere rating, and then we have a PT set which feeds the corresponding voltage 380:110. So, this is just like a typical power system arrangement, and these currents and voltages are fed to the relay, and the relay takes the decision, and the corresponding trip decision is being transferred to the trip coil of the circuit breaker, which opens in case the trip signal is being received, and if the trip signal is not received, the corresponding line still is in the energized states and feeds the corresponding load. So, this is the background how we verify the corresponding performance of the distance relay. So, what you do here, that in this transmission system at different points we create faults. As you see here, we can create phase A to ground fault, double phase to ground fault, double phase fault or 3 phase fault, all kinds of faults at different positions. Now, if we create 3 phase fault, then the amount of current flowing in the system in the lines will be much higher, and that should not cross the limit of the particular arrangement, otherwise fuse will be blown out. At the upstream, or the circuit breaker will trip, you can say, in case of this if it is a fault in the particular inside the zone 1 or zone 2 as per the setting of this one. The purpose here is that we are verifying only zone 1. So, the corresponding settings for the relay is being accomplished for zone 1 only. What we have here, that the line parameters, as I said, that the lines are made of 3 coils inductances, and these inductances as each are having 91 millihenry, and they are made up with a resistance of this copper wire having 2 ohm. So, the line impedance happens to be in total 28.64 ohm, and this is 1.7 J 2 pi 0.091 as you can calculate from that perspective. So, zone 1 setting of this particular protection of the line, we have said 80% of ZL, that comes out to be from here 22.9 ohm, and the CT considered here is 25:5 and the PT considered is 380:110 volt. So, we will see now the experimental setup on the table. The transmission line, these 3 transmission line sections for different 3 phases are available here. So, this is one coil for phase A, the second coil is here in phase B, and the third coil is here for phase C. And if you see here, we have different connection points at the intermediate points to create faults or to connect different loads. So, this line is being fed from this 3 phase supply from this switch and through this corresponding circuit breaker arrangement, and this is being connected to the load, and the load connected is the 3 bulb loads for the 3 phases. Now, to create fault for this system, we have switches here. So, they are being connected to the transmission line, and by switching any of the switch, we can connect the corresponding phase A, phase B or phase C, and also the ground in this perspective. So, these are the 4 switches to create different kinds of faults for the arrangements. Further, as you see here, these are the set of CTs, 3 CTs, which takes the corresponding current information, and they are being connected to the relay for the current information, current signals. And we have 3 PT, the corresponding set of PTs, which is being connected to the corresponding voltage terminals for the relay connection. Here in this case we have this REL 511 distance relay, and the relay is being connected to this PC to have the different settings and to see the different recordings during fault and so, and which like to demonstrate next for the experiment. Now, we have this demonstration. So, in this case first we will see that how the connection is being achieved and how the corresponding relay takes the data, and we will try to verify data that during normal time the relay is able to sense the corresponding current and voltages correctly or not, and the corresponding PT and CT values are being given input to this one. So, the relay will now be able to, at this loading condition, the ball loads are there, the corresponding supply is being fed to the transmission system, and at the transmission system the load is being connected. So, during this time if you see here the corresponding load current happens to be 0.335. So, here also the corresponding the clamping ammeter also showing 0.3 ampere. So, the current is in agreement with the external current, and the voltage here is showing 0.429 kV, and that corresponds to 429 volt. So, therefore, the 3 phase supply of the system, the corresponding with the arrangement of the PT and CT, the relay is able to correctly monitor the systems, correctly getting the voltages of this system side, the power system side, which is being connected to the relay. Now, we will demonstrate the fault in zone 1 and how the corresponding relay performs, we will see. For that, as already mentioned, that we have the corresponding transmission system which is connected to the load, and in the transmission system we will create fault. Here in this case we will create a fault phase B to ground and see how the corresponding fault in zone 1 the corresponding relay performs. For that I am creating, this is phase A, phase B and phase C. So, I am creating fault in phase B, and then we will see how the corresponding relay performs. So, we see that the corresponding relay trips successfully, and the corresponding breakers also opens, the corresponding load is switched off. So, the transmission line is being unorganized in this case, and therefore, the relay perform successfully correctly for the zone 1 fault. Now, for this case we will see the corresponding details provided by the relay to the PC, and see how the corresponding decision is being taken, how the what is the corresponding relay decision time, and what is the corresponding circuit breaker time, which zone 1 how much time it took, and so. Following the trip decision by the relay now provides the data through its recording, we call disturbance recorder. Now, the disturbance recorder, all the oscillograms and the trip decision we can see on the screen of this PC. So, we will see here now for this event, we see here we have markers. So, we have phase A voltage, phase A current, phase B voltage, phase B current, phase C voltage and phase C current. Now, these voltages and currents if you see here clearly, the currents in phase A has not gone up anywhere. In phase B, you notice here the current has gone up here. So, this is the point of fault inception. So, this marker shows the corresponding RMS value to be 27.73 ampere. Now, this is the corresponding relay decision time. So, from this fault inception to the relay decision time, this marker you see here, if you see here this zone 1, zone 2 and zone 3, they all started here at the same instant, true, and then for this one the zone 1 tripped here, no more zone 2 and zone 3. So, the zone 1 tripped here successfully. So, you see here for this one, from this inception of the fault to the zone 1 trip, the corresponding time difference is already clear here 30 millisecond. So, in 30 millisecond the corresponding relay trips. This is 50 hour system. So, this is trip time becomes 1.5 cycle exactly. Now, after this if you see the corresponding marker, if we take the positions to the till the fault is being cleared by the circuit breaker. So, the total time from the fault inceptions to the fault clearing by the circuit breaker, this happens to be 55 millisecond, because the current becomes here 0, and if we take this corresponding marker to this, then the corresponding the breaker time opening becomes 25 millisecond. In overall, we see that the corresponding after that the corresponding fault is being cleared. We see here all the three currents becomes 0 supplied to the particular load side. So, the corresponding experiment clearly shows that the zone 1 operates successfully, and it operates the corresponding breaker in 1.5 cycle 30 millisecond, and the breaker opens in 25 millisecond for this case. So, like this for different faults in different phases, we can create in the system in the our 3 phase line at different locations, and we can observe the performance of the relay for various system conditions, various types of fault and at various location. During the fault, if you see here the corresponding voltages and currents are being provided. So, the fault is in phase B. So, the corresponding fault current in phase B corresponds to a value RMS value of fault current shows 28 ampere, and then we have the corresponding voltage at that time. The RMS value of voltage happens to be 242 volt for this particular phase B. So, using these voltages and currents, we can find the corresponding Z apparent impedance for the particular case, and which we like to verify that whether it is a zone 1 fault or not. Now, we will create a fault outside the zone 1. So, that will be at the end of the line in this arrangement, and again we will be creating fault in the phase B to ground fault. In that situation, we will see that how the corresponding relay performs. So, we see that because the relay is now set only for zone 1, the relay should not for zone 1, that we should observe. So, the fault will continue. In that case, if the corresponding fault happens to be in phase B, then the phase B short circuit means then the phase B load should be getting 0 voltage or very low voltage. So, we will be verifying that, and we will see that how the relay corresponding performs in that kind of thing. During that situation, because there is no fault, so the that disturbance will not be recorded by the relay. So, therefore, from the monitoring perspective, we will see the corresponding different current and voltage, and that will be using for in our subsequent calculations to verify that what is the corresponding impedance the relay has seen, and during that time whether it has taken the decision correctly or not. So, let us now go for this creating fault in phase B to ground fault at the end of the line. So, we see here by creating this fault, the phase B bulb no more glows, where the other two phases are remain intact and the fault is continuing. So, we have created fault at the end of the line. So, the corresponding current here increases substantially. The corresponding current here it becomes 2.921, and this is the positive sequence current recorded by this relay, and the corresponding voltage here happens to be 429 kV, and this is line to line voltage. So, using this corresponding voltage and the corresponding current, we will be evaluating the corresponding relay performance. So, we see that for this one in zone fault and one out of the zone fault two situations, like this we created several faults for these systems, and then we will see that how to calculate and verify that the relay has operated correctly for the different situations or not. So, we took several observations for the in zone fault and out of zone faults and verify that the relay performs correctly in all the cases. So, the calculation process, the verification process we will now see. So, for the first case phase B to ground fault. So, we created a fault at 60% of the line and that is in zone 1 because our setting is at 80% of the line. So, this is what the corresponding oscillogram, the recording provided by the relay at that time. So, we calculated this apparent impedance for the phase B to ground fault using the relations V B upon I B plus K naught I naught, where K naught equals to Z 0 minus Z 1 upon Z 1. But as already mentioned, because the line which we have created here in the lab experiment purposes, the Z 0 is here equals to Z 1, which does not happen so in a typical line. Z 0 is lies between 2.5 times to 6 times typically. So, for this case the arrangement the Z 0 happens to be equals to Z 1 equals to Z 2. So, therefore, the K naught happens to be here 0. Using that relations, the apparent impedance here happens to be the corresponding voltage to 39.3 upon the corresponding I V current happens to be 13.73 and this gives you 7.42 ohm. But the actual impedance up to the fault, as we have created 60% of the line 0.6 and the line impedance being 28.64 happens to be 17.18 ohm. So, we see that the apparent impedance computed by this corresponding relay during the fall 17.42 versus the actual one happens to be 17.18. So, they are almost at par with all uncertainties in the response of the CTs, PTs and the calculation process in the relays. So, in overall we see that the apparent impedance happens to be 17.42 and that is less than the setting, that is 0.8 into the corresponding 28.64 happens to be 22.9. So, this concludes that the apparent impedance computed by the relay is correct and the tripping by the relay for the zone 1 is also correct. Next, we will see for the out of the zone fault which same you can phase B to ground fault which you created, and at that time the corresponding voltages and current measurements are shown from the screenshot of this one, because this is not being a fault recorded by the relay, it does not record in its it does not record. So, therefore, from these values of measurements we will calculate the corresponding thing and we see that the corresponding line voltage being 421 and the point sequence current shown by the relay is 2.859 for this case. So, the for this being the phase B to ground fault, a phase to ground fault only. So, I 1 happens to be equals to I 2 happens to be equal to I 0. So, therefore, the corresponding I B happens to be 3 times of this I 1 and as already mentioned K naught happens to be 0 and so therefore, the apparent impedance calculated by this relay during this time using the corresponding voltage and current we found the corresponding impedance to be seen by the relay happens to be 28.34 ohm. The actual line impedance ZL happens to be 28.64 and because the fault is being created at the end of the line that the relay should able to see 28.64. So, if we compare here that the apparent impedance seen by the relay is 28.34 versus the actual one 28.64. So, thus the relay computes the corresponding apparent impedance pretty correctly and it takes no trip decision for the zone 1 and that is also correct. So, in overall we see that the relay performs correctly for this situation also. So, in overall in this experiment we verify that the zone 1 fault in zone fault and out of the zone fault we created fault for the zone 1 only and we tested that the relay performs correctly for all the situations for zone 1 setting and the corresponding faults. Similarly, one can test for zone 2 and zone 3 faults at different creating faults at different position on the different lines, and so one can go for different types of fault also, phase B to ground, phase A to ground or 3 phase fault and so, and we see that the REL 511 the ABB MAC relay performs correctly for the line protection, particularly for zone 1. Thank you.